The minimum grounding rod size is 5/8 inch in diameter and 8 feet in minimum length. One grounding rod is sufficient for single-family residences and most commercial buildings. If two grounding rods are used, they should be at least 6 feet apart. Aluminum wire is still permitted for use in electrical service under certain conditions. Aluminum wire is generally larger in size than copper wire because it has a higher resistance. Aluminum wire must be installed correctly to prevent overheating and fire hazards. The grounding rod should be driven into the ground until its top is at least 2 inches underground. The grounding rod should be in contact with damp earth for optimal conductivity. The grounding rod should be connected to the grounding electrode conductor, commonly called the GEC, using a grounding clamp. The GEC should be run to the ground bar in the electrical panel. When dealing with grounding electrodes, several factors determine their effectiveness and compliance with electrical codes like the National Electrical Code, often referred to as the NEC. These factors include the type of electrode, its size, installation depth, and connection methods. Grounding electrodes play a crucial role in providing a low impedance path for fault current, thereby protecting people and equipment from electrical shock and damage. The NEC specifies various types of grounding electrodes, including ground rods, ground plates, underground metallic water pipes, and concrete encased electrodes, also known as UFA grounds. Each type has specific requirements for size, material, and installation. For ground rods, which are a common choice, the NEC mandates a minimum diameter of 5/8 inch for steel or iron rods and a minimum length of 8 feet. These rods must be driven into the ground to a depth of at least 8 feet, ensuring that a significant portion of the rod is in contact with the earth. This contact is essential for providing an effective grounding path. When driving ground rods, it's important to consider the soil conditions. Rocky or dry soil can impede the rod's ability to make good contact with the earth. In such cases, using multiple ground rods spaced at least 6 feet apart can improve the overall grounding effectiveness. The NEC also allows for the use of alternative grounding methods, such as ground plates, which must have a surface area of at least 2 square feet and be buried at least 30 inches below the surface. Underground metallic water pipes, if available, can also serve as grounding electrodes, provided they meet certain criteria, such as being in direct contact with the earth for at least 10 feet. Concrete encased electrodes, or UFA grounds, are commonly used in new construction. They consist of at least 20 feet of bare copper conductor encased in concrete that is in direct contact with the earth. These electrodes provide excellent grounding due to the large surface area in contact with the soil. The grounding electrode conductor, or GEC, is the conductor that connects the grounding electrode to the electrical panel's ground bus. The size of the GC is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. It's crucial to use the correct size GC to ensure that it can safely carry fault current back to the source. The GC must be securely connected to the grounding electrode using approved methods such as grounding clamps or exothermic welds. These connections must be corrosion resistant and provide a reliable electrical connection. In addition to the grounding electrode and GEC, other grounding components play a vital role in the overall grounding system. These include the equipment grounding conductors, which connect the non-current carrying metal parts of electrical equipment to the ground bus in the electrical panel. Equipment grounding conductors provide a low impedance path for fault current, helping to trip circuit breakers or fuses in the event of a ground fault. Ground fault circuit interrupters, or GFCIs, are another essential safety device that protects against electrical shock. GFCIs monitor the current flowing in a circuit and quickly interrupt the power if they detect a ground fault. They are commonly installed in bathrooms, kitchens, and outdoor areas where the risk of electrical shock is higher. Proper grounding is essential for electrical safety and is required by electrical codes. A well-designed and properly installed grounding system helps to protect people and equipment from electrical hazards. Regularly inspect the grounding system to ensure that all connections are tight and corrosion-free. Replace any damaged or corroded components to maintain the integrity of the grounding system. Aluminum wire has specific considerations in electrical installations. While aluminum is a good conductor of electricity, it has a higher resistance than copper. This means that for the same current carrying capacity, an aluminum wire must be larger in diameter than a copper wire. Aluminum wire is also more susceptible to oxidation, which can increase its resistance and lead to overheating. To prevent these issues, aluminum wire must be properly installed and terminated. When using aluminum wire, it's crucial to use connectors and terminals that are specifically designed for aluminum. These connectors are typically made of aluminum or are coated with a corrosion-resistant material to prevent oxidation. They also provide a larger contact area to reduce the risk of overheating. Antioxidant compounds should be applied to the aluminum wire before making connections. These compounds help to prevent oxidation and ensure a good electrical connection. When tightening the connectors, it's important to follow the manufacturer's torque specifications. Over-tightening can damage the wire or connector, while under-tightening can result in a loose connection and overheating. Aluminum wire should be inspected regularly for signs of corrosion or damage. If any problems are found, the wire and connectors should be replaced immediately. The NEC provides detailed guidelines for the use of aluminum wire in electrical installations. These guidelines cover conductor sizing, termination methods, and other important considerations. Adhering to these guidelines is essential for ensuring the safety and reliability of electrical systems. When working with electrical systems, it's always best to consult with a qualified electrician. The electricians have the knowledge and experience to ensure that electrical work is done safely and in accordance with electrical codes. They can also help to troubleshoot electrical problems and make repairs. Electrical safety is paramount. Always turn off the power before working on any electrical equipment. Use insulated tools and wear appropriate personal protective equipment, such as gloves and eye protection. Never work on electrical systems when you are wet or standing in water. If you are not comfortable working on electrical systems, hire a qualified electrician to do the work for you. Grounding systems are designed to provide a safe path for electrical current in the event of a fault, protecting people and equipment from electrical shock and damage. The effectiveness of a grounding system depends on several factors, including the type of grounding electrode used, the size and material of the grounding conductors, and the quality of the connections. There are several types of grounding electrodes commonly used in electrical systems, including ground rods, ground plates, and underground metallic water pipes. Ground rods are typically made of copper or copper-clad steel and are driven into the ground to provide a low-impedance path for fault current. Ground plates are metal plates that are buried in the ground and connected to the grounding system. Underground metallic water pipes can also be used as grounding electrodes, provided they meet certain requirements. The size and material of the grounding conductors are also important factors in the effectiveness of a grounding system. Grounding conductors must be large enough to safely carry the maximum fault current that could occur in the system. They must also be made of a material that is a good conductor of electricity, such as copper or aluminum. The quality of the connections in a grounding system is critical to its performance. All connections must be tight and corrosion resistant to ensure a low impedance path for fault current. Loose or corroded connections can increase the resistance of the grounding system, reducing its effectiveness and increasing the risk of electrical shock. Ground fault circuit interrupters, or GFCIs, are another important safety device that can help to protect people from electrical shock. GFCIs monitor the current flowing in a circuit and quickly interrupt the power if they detect a ground fault. They are commonly installed in bathrooms, kitchens, and outdoor areas, where the risk of electrical shock is higher. Electrical codes require that all electrical systems be properly grounded. Grounding requirements vary depending on the type of system and the location. It is important to consult the applicable electrical codes and standards to ensure that your electrical system is properly grounded. Regular inspection and maintenance of grounding systems are essential to ensure their continued effectiveness. Grounding connections should be checked periodically for tightness and corrosion. Grounding conductors should be inspected for damage or deterioration. Any problems with the grounding system should be corrected immediately to maintain its safety and effectiveness. When working on electrical systems, it is important to follow all safety precautions. Always turn off the power before working on any electrical equipment. Use insulated tools and wear appropriate personal protective equipment, such as gloves and eye protection. Never work on electrical systems when you are wet or standing in water. If you are not comfortable working on electrical systems, hire a qualified electrician to do the work for you. The use of aluminum wire in electrical systems has been a topic of debate for many years. Aluminum wire is less expensive than copper wire, but it also has some drawbacks. Aluminum wire is more prone to oxidation and corrosion than copper wire. This can lead to loose connections and overheating, which can cause fires. Aluminum wire also expands and contracts more than copper wire with changes in temperature. This can also lead to loose connections and overheating. Despite these drawbacks, aluminum wire is still used in some electrical systems. When aluminum wire is used, it is important to follow certain precautions to minimize the risk of problems. Aluminum wire should be properly sized for the load it will carry. Aluminum wire should be terminated with connectors that are specifically designed for use with aluminum wire. Antioxidant compounds should be applied to the aluminum wire before making connections. Aluminum wire connections should be checked periodically for tightness and corrosion. The NEC provides detailed guidelines for the use of aluminum wire in electrical systems. These guidelines cover conductor sizing, termination methods, and other important considerations. Adhering to these guidelines is essential for ensuring the safety and reliability of electrical systems. If you are considering using aluminum wire in an electrical system, it is important to consult with a qualified electrician. An electrician can help you to determine whether aluminum wire is appropriate for your application and can ensure that it is installed properly. Understanding the requirements for grounding rods and the proper use of aluminum wire is crucial for ensuring electrical safety in residential and commercial buildings. By adhering to the NEC guidelines and best practices, you can minimize the risk of electrical hazards and protect people and property from harm. Proper grounding and wiring techniques are essential components of a safe and reliable electrical system. Remember to always consult with a qualified electrician for any electrical work to ensure it is done correctly and safely.